Bisogna disattivare l'audio del portatile. Non mi sta...
Ok, possiamo cominciare, Alessandro?
Sì, c'è qualche problema da casa con l'audio perché bisognerebbe disattivare l'audio del portatile. Ma in teoria comunque in questo momento da casa mi dovrebbero sentire. E quindi anche quando parli tu dal microfono dovrebbero sentirti. Quindi
Ok,
provate e da casa ci diranno se sentono o no.
ok, allora direi di cominciare. So I switch to English. Thank you very much to all for coming. This is our Christmas lecture 2025. I'm speaking on behalf of the directors of Institute of Radio Astronomy and the Department of Physics and Astronomy of the University of Bologna. And I am the director of the Observatory of Space Science and Astrophysics of Bologna. We belong to the National Institute for Astrophysics. So it's a great honor to have here this year a key person of the ESO, so the European Southern Observatory Organization, Michele Cirasuolo, who was formerly science program manager of the ELT, Extremely Large Telescope, a main enterprise in modern astrophysics, and now is the overall director of the instrument program at ESO. So it's, I would say, the perfect person to provide us with an update, an overview of the development of the instrumentation from VLT, Very Large Telescope, to the ELT, which aims at being it will be the largest telescope in the world. So we are really living in a golden era of astrophysics with great missions like JWST in orbit, ELT under construction, I would say now under advanced construction. So in the very next years, we hopefully will be operative. We will hear from Michele. And again, what Michele is going to present to us shows one more the great synergy between science and industry, which I think is really something we have to stress more and more to the society. So once more, investing in these astronomical enterprises means investing in the industry, in progress, in technology, having a double benefit, cultural benefit, progress of our knowledge of the universe, but also a lot of technological developments that will benefit the life of all of us in the next years. So I leave now the floor to Michele. Thank you very much.
Grazie. Thank you for inviting me here. It's an honor, a pleasure to see old friends, my teachers, the people that really taught me how to do astronomy and astrophysics. They are here in the room. So it's really an honor to be back to Bologna. It's always in my heart. And that's where I learned really how to do science. So what I would like to give you today, it's a brief overview of what's coming in terms of instrumentation and science, particularly from the ESO point of view. And I would like to start from ESO itself. So ESO is an intergovernmental organization. And the mission of ESO, you will see it here, is to design, build, and operate advanced ground-based observatories. The idea is really to build with the community these facilities, but not for the sake of them, but to really get the advancement of science. And that is our vision. So really advance our understanding, working with the community through science. That's what Lorenzo was saying before. We work not only with the scientific community, but also with the industry and the actual world around us. ESO is today composed by 16 member states, was founded by 5 of them in 1962. As you can see there, all the member states are mostly in Europe. All our telescopes are in Chile, and I'll show you later some more details about it. And the headquarters is in Germany, nearby Munich. And we have at the moment a strategic partnership with Australia, which will expire in 2027, hopefully will be renewed as a full member state. But that is the ecosystem of ESO. So all this country working together to deliver the science. As I said, all our facilities are actually in Chile, in the Atacama Desert, in the north of Chile. And that is because, as you can see from this view, you have the Andes, so very high mountains from 3,000 to 5,000 meters just nearby the sea. So you have this very, very clean sky. And as you can see, is an absolute desert up there. So the conditions are optimal for astronomical observations. And here is where we are building our, essentially, a science park. This is the valley between Cerro Paranal, where we have the Very Large Telescope. 25 kilometers inland, we have Cerro Armazones, where we are building the Extremely Large Telescope. In the valley in between, there is the Cherenkov Telescope, CTA South, and we'll cover all the area in the middle, in between the two observatories. And then we have further up in the north, 500-600 kilometers in the north toward Chaknantor, where we have an even higher plateau of 5,000 meters, where we have the ALMA Observatory. And then in the south, again, a couple of thousand kilometers southern than here, there is La Silla, which is the original birthplace of all the ESO telescopes. That's where ESO started putting smaller telescopes, and now we have there of the order of 10-ish facilities. Two of them are 4-meter class telescope, the NTT and the 3.6 meter. But what La Silla is used today is more as a ground for the member states to place their own experiments. So if anyone in the community wants to have an idea for a small telescope, they can come to ESO and use La Silla as a ground for their facility, which is an experiment. So ESO does not run it, so the country runs this, but ESO provides the facilities around it. So if you have ideas on how small facilities or small telescope can be run, we have La Silla for this. But overall, this is what ESO does. So particularly VLT and ALMA, CTA is coming, and also the Extremely Large Telescope, which I'll give you more detail later. But before going to the detail of ESO, I would like to give a bit of a landscape. So where are we today? So in the astronomical instrumentation and facilities, we have a lot of space facilities. HST, JWST, Euclid, Cheops, and ESA is continuously increasing the number of space missions that are for astrophysics, both in the solar system, but also for astrophysics. If you look at in the ground, I went one too far, there is plenty of 8 to 10 class meters. So we have the VLT, but also there's the Keck on Mauna Kea, Subaru. We have the 2 Gemini, Gran Tecano in La Palma. So there is a variety of 8 to 10 class meter telescopes, which I've been pushed to the edge of their facilities, the edge of their integration time over the last 20 years, and are still up and running. And then if you look at longer wavelength, we have all the radio facilities like LOFAR, EVLA, the precursor of SKA like ASCAP and MIRCAT, and of course ALMA, NOEMA. So you have all these sub-millimeter, millimeter, and radio facilities which are up and running and providing a lot of science. And also in the last decade, we also have seen a lot of increase in the observations of gravitational waves. So we don't look at the electromagnetic part of the spectrum, but to the gravitational change of the space-time. And we have LIGO, Virgo, Chakra. So there's a lot of new science coming, particularly for the multi-messenger, into this gravitational wave astrophysics. That's what we have today. And of course, the king of the last few years has certainly been JWST. Has revolutionized many of the astrophysical fields, from exoplanet to galaxies. And just for you to remember, because you will see these numbers later, so James Webb is a 6.5 meter telescope. So it's 2.5 times larger than HST, so better resolving power, is in space, so very low background, and allows you to go up to 27 microns. So allows you to go into the mid-infrared, which is very difficult from the ground. And as you see, there is a comprehensive suite of instruments, most of them working in parallel, which gives you a very good facility. But the number I want you to remember is this diffraction limit, which is 65 milliarc second at 2 microns. So in K-band, the angular resolution of James Webb is 65 micron, which is of the order of what you can get with the VLT if you apply adaptive optics, okay? Because just is driven by the diameter of the primary mirror. That's what we have today. So what is the landscape in the next few years? So certainly in the next 5 years, we're going to have an explosion of data coming both from imaging and spectroscopy. Certainly, we have the Vera Rubin that will provide deep imaging in time domain. Euclid will provide all the surveys in the near infrared, and hopefully also Roman, which is the American equivalent of Euclid, will hopefully come soon online. And what they will produce is essentially a cosmic atlas. You're going to get for the very first time sharp images a la HST, but over the entire sky. And it gives us both in the visible and in the near infrared with a time domain attached to it. Because mostly LSST or Vera Rubin, as well as the near infrared part, especially in the deep fields, will give you all the transient universe. Vera Rubin claims to have millions of alerts every single night. So you have to start picking which one is more important for your science to then do spectroscopic follow-up. And for this spectroscopic follow-up is something that is really another big mine that is coming in the next few years. There is a series of multi-object spectrographs and surveys that are coming online right now. So there's Moons on the VLT, Foremost on Vista, DAISY, PFS, and Phobos on Keck. And as you can see, all of them try to cover either the visible and part of the near infrared, and they do it in a variety of resolving power. Usually a medium resolution of the order of 5,000, 3 to 5,000, mostly for extragalactic science. And then you have some of them pushing this to 20,000 to get the chemical tagging for stellar astrophysics. And as you can see, this is a quite large multiplexing of several thousand per shot. And what this gives you is access to a variety of science where you need spectroscopy, but also need statistics, because that's where you need to have a large number of objects to really get the physics out of it. For example, if you want to understand the chemodynamical properties of stars in our own galaxy, either in the external part or in the central part of the bulge of the galaxy, you need thousands, if not millions of spectra of stars of different type in different regions to understand how our own galaxy formed. But of course, you want to push this to the higher universe and then understand how galaxies evolve across time, both in terms of physical, but also chemical and dynamical properties for the galaxies. But also you want to understand cosmology. You want to understand the nature of dark energy, dark matter. So you need massive spectroscopic survey that allows you to have a large statistical sample, hopefully well calibrated, to make the understanding of the universe. Now, going more into the ESO facilities, so I want to focus on two instruments, particularly. So one is Foremost, which goes on Vista. It's a 4-meter telescope, which sits in Paranal on the peak, kilometers away from the actual Paranal, from the VLTs. And Foremost has been in construction for the last 10 years, and now finally has been commissioned. And now on the 18th of October, we had first light. The first spectra came in. The instrument is fully installed at the telescope. The full 2,500 fibers are working. And soon, as soon as we finish the commissioning, we will start a huge amount of science, because Foremost is a community-driven survey. So we have a variety of different surveys, which are either GTO time, but also community open, which will tackle a variety of science cases, from galactic archaeology, following up Gaia and preparing for Plato, also looking at galaxy evolution, where you have deep components over a smaller part of the sky, where you go deeper, still in the visible. All the follow-up of the high-energy universe, particularly focusing on Rosetta, but also looking at providing follow-up for Euclid, LSST, and SKA to provide a more cosmological understanding of the universe. And then I would like to spend a few more words on another instrument for which many people in this room are also connected, particularly me, because I've been the PI for this instrument for the last 10 to 15 years. You can see here, Moons is a near-infrared spectrograph compared to Foremost, which is a visible. Moons is a near-infrared instrument, so you need to keep your entire instrument to a cryogenic environment. You can see there on the right, the cryostat, which is the largest in modern astronomy. It's 4 meters tall by 3 meters wide by 3 meters deep. It's a massive cryostat where you have all the optics in there, which are large. And to pick up the 1,000 objects we have on sky, we have developed a new technology of small fiber positioners that are able to move very accurately on the focal plane, dancing around each other, not to collide, but to pick up very precisely to a level of few microns on the focal plane to get the targets. And this is also finished, it's completed. We are shipping it. We shipped last week. So we need to it will arrive in Paranal very soon. And because MUNS is a near-infrared instrument, the idea here is more to go in more different areas compared to foremost, for example, doing galactic archaeology, but in regions which are more obscured. So the central part of the galaxy, the bulge and the disk, where the near-infrared information is the one that comes out because the visible is obscured by dust. But also looking at obscured black holes and getting the physics of galaxies, particularly looking at the environment. So the idea is we build on 300 nights of GTO time, of which 100 are dedicated to this survey in our own Milky Way. As you can see here, the various pointings, where the idea is to target the central part of the galaxy, to get chemical abundances and radial velocity in the central part of the galaxy, and getting the extragalactic part for 200 nights, the equivalent of 2 million fiber hours on an 8-meter class telescope, to get diagnostics for both passive and star-forming galaxies at the same wavelength range rest frame that you use in the local universe with SDSS. So the idea is to compare apple with apple. So if you have a local survey where you have oxygen and H-alpha, H-beta, you want to track the same lines also high res, so you can compare the evolution of these physical and chemical properties of galaxy as you go across the universe, but also looking at the environment. So the survey is designed to have a high completeness. We want to tackle all the possible groups or companions or the environment, if you are in clusters or not a high redshift, to see how much there is an interplay between the physical properties and the environmental part, how much the nature and nurture are shaping the formation of galaxies. So that's what we have in the next let's say 5 years, but what's coming next? What is the next future in the next, oh, way too fast, it's so sensitive today. So the next 10 years from 29 to 39. So the landscape is certainly, we have this facility running, we're gonna have LSST, JWST, Euclid, massive spectroscopic surveys. We're gonna get ESA missions for science in terms of exoplanet, both Plato and Ariel, which will provide many candidates and some characterization of the atmosphere. We're going to have SKA, hopefully operational, possibly NGVLA, we don't know. In terms of missions from ESA, we might have LISA and New Athena, near to launch or launch, possibly Theseus, fingers crossed, that is selected. But we might also have some retired mission, right? So Hubble, by then, is going to be 40 years old. So it's running on the edge. So something might happen on NASA, and also some X-ray facilities might be on the end. So the landscape then is evolving. So we might have new facilities, but moving away from some of our famous instruments. On the ESO side, what's up on the same time scale? ALMA, as I showed you before, is going to be upgraded. There's a big program in ALMA to expand the wideband sensitivity. The idea of is to increase the bandwidth, which allows ALMA to observe simultaneously by a factor 4 in all the various bands. Today, ALMA is limited by how much you can observe simultaneously, especially when you do scans. The idea is to expand this by a factor 4 by improving the correlator, but also some other hardware within the observatory. So that it's happening. But at the same time, we need to continue running what is the VLT and the VLTI. And that is a snapshot of what we have in Paranal. So these are the 4 telescopes, the 4 UTs. Each one of them has got 3 foci. So we can have 12 instruments in total just in the VLT. And this is the landscape that we have. Each of the foci is equipped with a specific instrument. Together, all of them, they cover most of the parameter space. We cover imaging in the visible, UV, near-infrared and mid-infrared. We do this with various filters. We do this in polarimetry. We have spectroscopy, both a low resolution, medium resolution, high resolution. And this is all provided to the community by proposal. So you can apply to any of these facilities depending on your science. You can go and pick your specific instrument in the VLT. But also this telescope can work as a unanimous. So the 4 telescopes of the UT were thought from the very beginning to work as a single telescope, either in a non-coherent way, for example, by using espresso. So you combine the light of the 4 telescopes without taking care if the light is coherent. You're not doing interferometry, but you're using the 4 UTs as a light bucket. And this light is then through fibers conveyed to espresso, which is in the CUDE room below the telescopes. And there you have a very high resolution spectrograph, 100,000, to mostly do exoplanet search. And that is a non-coherent way of using it. But the VLT has also been designed and built to do VLTI, so real interferometry in the visible, particularly near infrared in this case, where the light between the various foci is combined in a coherent way, like you do in radio. Essentially the same thing. Much more difficult because in radio, the waves are very long, so much easier to correlate. In the visible, you have to mechanically make sure that the light is correlated. So you have all this delay line underneath the tunnels or between the 4 telescopes that are combining the light in a coherent way to give you very high resolution. So essentially, because you do interferometry, you end up with a telescope which is essentially 100 meters. The distance between the 4 telescopes gives you the baseline, and therefore you end up with a 100-meter essential telescope. And we have 3 instruments there, Gravity Plus, Matisse, and Pioneer. And as you can see in the images on the background, now we have equipped all UTs with lasers. So this facility, particularly for the VLTI, they are all working in adaptive optics. All of them have got lasers and adaptive optics for them. And in the future, we will continue developing new instruments. So we're just signing a contract for Blue Muse, which is the blue extension of Muse on one of the UTs. We are building another thermal mirror for a telescope. We have already instruments like MAVIS, cubes already online. And all these instruments are now in final stage of production, like MAVIS and cubes, and new ones are coming. And particularly, we're going to have a workshop in January at ESO, if you're interested, for building the new facilities for the VLT. Once we've done this, we need new ideas, especially for the young people. What do you want to do in the future? What are the science that you want? And therefore, which instrument we have to make for you to make your own science? So if you're interested, please let me know. There is this workshop in January at ESO. Please come and listen and give ideas on how to do it. But overall, what I showed you so far has been somehow traditional. We have already this 8-meter class telescope. We've been using VLTI for several years. But what was missing was the next generation. What's coming next? The VLT and all the 8 to 10 class meter over the last 10 to 15 years has been pushed to the edge. We had integration of 100 hours, for example, in some of these telescopes to push to the edge of what we could do with an 8 to 10 class meter. So 15 years ago, so ESO started a new project to really push this to a next level from an 8 class meter, much, much bigger, which is the very unconventionally in ESO land. You go from a very large telescope to an extremely large telescope, just because the naming convention at ESO is very funny. And they even started with an overwhelmingly large telescope, which went down to an extremely. And here, the telescope is essentially the biggest eye in the sky. 39 meters in diameter, the primary mirror, which is going to be the largest optical infrared, larger even than the American competition from TMT and GMT, which are 30 and 25 meters. So the ELT is going to be the largest and is the one which is in construction now. As I'll show you later, is in a very well advanced state. As I'll show you later, the ELT to operate and function needs to have adaptive optics already built inside the telescope. It's so big and is so complex that you need to build adaptive optics inside. I'll give you a few slides later. The project or the program start already with some phase A's at the beginning of the decade, but the real green light with all the funding and all the money came in 2014, a council. So all the funding is approved. The work is well underway. There's a good comprehensive suite of instrumentation. And today the first light is foreseen for 2029. So for the young generation is your opportunity, right? So it's coming. So start thinking on how to use it. For many years, we've been using CAD modeling and drawings on how the ELT might look like. That is one of the video produced several years ago by ESO, but just give you an idea of how the telescope might look like. And that is made by a primary mirror, as I said, of 39 meters in diameter. Now, the largest mirror that you can make without any monolithic is 8 meters, right? If you want to go larger than that, you have to segment. You have to make small pieces of it. And actually, Guido Hord Arturo here in Bologna was one of the precursors of this. So learning how to segment a mirror and use it for astronomy. Now we push this to the extreme, right? But now we need 798 individual segments to make this primary mirror. And then we need 2 mirrors just for the relay optics, so M2 and M3. And then we have 2 mirrors there, which are special mirror. And I'll show you later more details. And these are M4 and M5, which are the mirror that gives you the adaptive optics, are the ones that do the magic to remove the atmosphere and essentially pushing the ELT above the atmosphere. These 2 mirrors allows the instruments to clean the entire air in front of them, all the vibration, all the disturbances, to give you very, very sharp image at the diffraction limit of the telescope. And we also use lasers to help this. So how does it work? The light bounces from the stars on M1, then goes to M2, M3 inside the tower, and M4 and M5 provide this magic before the light is sent on 2 of the Nasmyth platform. Each of those platforms is as big as a tennis court. So it's a massive thing. And the M2 is sitting at 80 meters above ground. And just to put into perspective, I know some of you have been there in the Colosseum. So the ELT is as large as the Colosseum, but twice as tall. And we don't kill any people in there, but in the ELT, we use PhD students to move the optics. So we need volunteers, especially the young ones, strong, go to the gym. We need you to help rotating that thing. Because for ELT, we have a big problem. The telescope is massive. The entire structure, just the stuff inside to host the telescope, is 3,500 tons. And this thing has to move and rotate as we track the sky. But at the same time, because we want to have very sharp images, this motion has to be super smooth. We cannot afford to have clunks, right? We cannot afford to have hysteresis in the system. So there is a lot of work done by the engineer to make sure these things move extremely smoothly across the entire motion of the telescope. And the mirror is huge, right? So that is in comparison between the ELT mirror, James Webb, and Hubble, right? So you can fit inside the hole of the ELT in the middle, both James Webb, and you can fit even a VLT mirror in there. And all these things, all the mirrors, which again, just for comparison, all this mirror needs to be phased and maintained to a given shape with an accuracy of 10, 20 nanometer. So imagine you have to maintain all these things, which is 3,500 tons. Each mirror itself is weighing 250 kilos, only the glass. And as you move across the sky, you have the gravity pushing down on each of these mirrors as you tilt it and you move it. But still, every single mirror from this side of the edge to the other side of the edge needs to be maintained to 20 nanometer accuracy wavefront error across the entire 40 meter diameter. And that is a challenge. And I guarantee you, there's a lot of very smart people thinking on how to control, measure, and maintain this thing under gravity, thermal, wind load, vibration. So there's a lot of work. So what I showed you before was just graphics, right? So you might think, so he's dreaming, right? It's just paper. It's never going to work. Impossible, right? It's not. It's reality. So for many years, we had, some of you have been there. Piero's been there to see only the top of the mountain. Now we are feeling the top of the mountain with real hardware, with real telescope. That is a view from far away. And that is a view closer up. That is the back of the telescope. You can see the big round around, they're called auxiliary building, is where we do maintenance. That's where we code the mirrors. That's where we have electronics, that we have things. And then we have here the back of the telescope with all the cladding on top. And that is a view from the front where you can see the slit door open. And that in the center there is the full complete structure without the mirrors, but all the mechanical structure is there, completed, and is actually moving, right? The beauty of this is now that the engineers have done such a good job that these mechanisms are moving without introducing vibration. The entire thing rotates. I have a video later, but the entire structure moves and the doors closes, and you can see here a picture of the door fully closed for the telescope. The cladding is almost complete. So by next year, the construction of the dome and main structure, as we call, will be completed, and we will start installing the mirrors inside. That is another view of the actual structure. And again, to put into perspective, that is a zoom in of someone on that structure, right? So how small? Each of those holes that you can see there will be filled by one of the 798 mirrors, okay? And the challenge of the mirror is large. There is a lot of work to be done onto these things where you have these pads, these yellow things is a launch pad for the lasers that we need for the telescope. There are hundreds of kilometers of cabling that needs to be installed inside the telescope. You can see here the people start laying down the cabling underneath the primary because we need electronics, we need cooling for all this massive structure. And we need to install the Nasmith platforms where you see this big half round. That is the side of the Nasmith port. That's where the instrument will be sitting as soon as we mount the Nasmith platform. They are 30 meters above ground. So don't forget anything when you go up, because otherwise you have to go down again. And don't have vertigo, because in these things, everything is super high, super big, a lot of stairs to go up and down. As I was telling you, the challenge is to build this primary mirror. So that in the center is a VLT mirror, 8 meters in diameter. And these are the 798 mirrors for the ELT, a massive scale up. They all start made by these, on the right, you can see here those discs. These discs are made of a special material called zero dur. The way in which we work with industry. So this zero dur was created for astronomy. We needed a material that had very slow or zero coefficient of thermal expansion. So as during the night the temperature changes, we don't want the mirror start breathing, right? We want it to be very stable. But we want a material that is very polishable. You don't want something that is very porous and doesn't scatter the light everywhere. So the industry was Schott, in that case, a German company, invented this material for astronomy. And now you have it all in your houses. And that is in your kitchen. So where you cook, the black piece of black material where you cook on, especially in induction cook, that is made of zero dur, or an evolution of zero dur. So something that was created for astronomy now is implemented in the house of many, many people to see how sometimes the invention for astronomy go back into society. In terms of production for this primary mirror, you can see there one of them fully finished and already coated with a very thin layer of silver, because it has to be very reflective. We have already 600 of them produced, and 300 of them are already in Paranal, coated and stored in this big warehouse that we have built in Paranal. So if you count 298 1.4 meter diameter mirror is already the largest telescope on Earth. It's not phased, but it's already the largest telescope on Earth by an order of magnitude compared to Grand Tecan, which only got 36 mirror, right? Then we need M2 and M3, the relay mirror that I showed you before, M2 and M3. Now, some of you have been to the Galileo telescope or to the Vista telescope. So that is a 4 meter diameter primary. So that mirror, the same size on the ELT, becomes a secondary mirror, which is sitting upside down in the huge cell, 80 meter above ground. Very complex shape for the convex mirror, had been polished down to 50 nanometer accuracy. That's 3 times better than the spec. And the company is very happy. Here they're testing it into the cell, and then it will be delivered to Chile beginning of next year. So that M2 and M3 M2 is finished, and M3 is on the way to be finished. Has been almost 3/4 polished, and we need to keep going with that one. And then we go to the core of the adaptive optics of the telescope. We do this first with a mirror which is called M4, which is a mirror in which you have a very strong background, a very strong substrate, which is made of silicon carbide. And there are 5,000 holes. In each one of those holes, there is a mechanical device that is able to pull and push on a very, very thin shell, which is 1.9 millimeter thick. And then the light after M4 goes to M5 for the final steering mirror. But the one that does the magic is M4. And the reason why we need this special mirror is because we breathe, right? We have atmosphere. We're all happy to be able to breathe, and everyone, especially when the air is good. But the atmosphere does something very strange or weird to the light that travels for sometime 13 billion years untouched, through empty space. Then when it arrives to the edge of our atmosphere, all the molecules, because they move and they have their own patch of motion due to thermal motion of the atmosphere, what they do, they distort the wavefront. So when the light comes to us, it's distorted by our own atmosphere. James Webb does not have this problem, right? It's in space, it doesn't have the atmosphere. But you can only build a 6 meter, right? On the ground, you can build a 40 meter. So if you are able on the ground to remove this effect, you gain, because you don't need to be in space, much more expensive. So James Webb costed 8 to 10 billion euros. The ELT only cost 1.5. So with the cost of James Webb, you can buy 5 or 6 ELTs, but you get discount after the first one, right? So the idea is when you are on the ground, what you get is an effect like if you are underwater, right? Everything in front of you blurs and you get this scintillation of the stars. So therefore you don't see very, very smoothly. But what you can do is to apply a technique which is called adaptive optics. What do? You observe a star. This star, is a point source. And if you observe the star very, very fast, sometimes 500 times a second or 1,000 times per second, what you can do is you can change the shape of the special mirror to counteract all the imperfection that the atmosphere have introduced. And therefore, your image becomes sharp again. Essentially, it's when you do the noise cancellation into your headphones, right? So the sound comes in, you measure how much is the sound of the noise, you apply the opposite, and therefore you cancel that noise. It's exactly the same idea, okay? And you can do this by using these very special mirrors, where you have this very thin shell, because it has to be thin, because it has to be able to move and change shape in a very, very controlled way. And you have this actuator behind that are able to pull and push onto the shape, again, in a very accurate way to the nanometer accuracy across all the shape in a very, very high control mode. So you can impose up to 4,000 modes with all this Zerniki way in which the AO people think. And if you have questions, go to the group of AO here in Bologna. They will tell you all about it. And we do this by looking at stars, but also we use lasers. To do this, you need a very bright star, because you need to be able to observe this star 1,000 times per second. So how many photons you can get in every frame is limited, okay? Because a single limit, you have to be able to do this. But what we do, we also use lasers. Both we do this on the VLT today, we do on the ELT. We shine lasers into the atmosphere. They react with the particles of sodium, which are in the 80 kilometers high up in the atmosphere, and they shine back in a very sharp, reasonably sharp way. And that helps us to make some of this correction. So we can use a fainter star and therefore apply this to a much larger sky coverage. If we only look at single stars without lasers, we cover 1 to 2% of the sky. If we use the laser, we go 80 to 90% of the sky. So I'm sure your favorite object is not lying close to a bright star by definition, right? Because my galaxy is the one that is far away from the star. In this way, by using lasers, we can compensate for this. And we can observe essentially everywhere in the sky. So essentially what we do is very blurred image to very sharp image, right? So essentially what we do, we remove the atmosphere as well as any vibration from the telescope itself. And that is at the core of the adaptive optics. And then once we do this, we go to the instruments. And the instruments are the ones that observe this light, but at the same time, they also help to make these corrections. You want to have the sensing of the AO very, very close to the science focal plane. And for example, we do this with Morfeo. It's led here in Bologna, so it's an honor to have an Italian instrument, which is the largest and most complex AO system ever built in astronomy. It's got not only using M4, which I showed you before, but it's got 2 extra post-focal DM, quite large. And that is controlling all this accurate modeling of the atmosphere, making corrections and providing very, very sharp images. So the PI and the project office is here in the room. So if you have questions, go to the Observatory of Bologna and they will tell you all about this. But it really is an honor for Italy to be able to build this kind of facilities. That is the most advanced AO system ever built. And then what it does is provide you high sky coverage and high sensitivity to feed 2 instruments. So we started with Mikado, which is an imager, providing imaging from 0.8 to 2.5 micron in various medium band, narrow band, and broadband filters over a field of view of 1 arc-minute, but with pixels which are tiny, 4 milliarc-second to sample the diffraction limit of the ELT, which is of the order of 10 milliarc-second, and also has got a single slit spectroscopy. And this picture is quite old, but we have Harmony, which is the integral field spectrograph. It gives you essentially for every pixel a spectrum, while Mikado gives you an image. Harmony gives you, for of course, a smaller field, but for every pixel, it gives you a spectrum at a resolution of 3 to 8,000, again with small spaxels. This image is old because now also Harmony is fed by Morpheo. So Morpheo is feeding the two most important instruments that we have at the ELT. And then for the people that are interested in the mid-infrared science, we also have METIS, which provides imaging from 3 micron up to 15 micron to the L, M, and N band, both in imaging, single slit spectroscopy, and IFU at 100,000 resolving power. And then these are the first bunch of instruments. And then we're starting also the second generation for Andes, which is a high resolution spectrograph, 100,000 resolution from 0.4 to 1.8 micron. And also this one is led by ENAF, particularly this time the PI is in Arcetri. And we have a multi-object spectrograph mosaic that will give you a multiplexing of 300 to 400 objects simultaneously, again, across the visible and the near infrared. If you are an astronomer, so what do you care? So how can I use these things? What are my parameter space? So if you look at the wavelength coverage as a function of capabilities, you can see that in imaging, you have Mikado and METIS, and then in spectroscopy, at various resolving power and various ranges, you have all the other ones, providing you up to 100,000 resolution. And how does it compare with James Webb? So James Webb is fantastic in very long range because you're in space, so the thermal background is very low. But in terms of short wavelength and resolving power, as you can see, the resolving power of James Webb is very low. It's very good for sensitivity, but if you want to get the physics, the astrophysics of targets, when you need to split the light and get the resolving power of individual lines, you need high resolution, and that's where the ELT comes in to provide you all these things. And the resolving power and the diameter of the ELT comes with two benefits. So one is sensitivity that goes with the diameter of the primary mirror, but to the fourth power, because you boost not only the area, but also because you are squeezing the light with adaptive optics, you put them on very, very small pixels, and therefore you gain twice. So you gain d to the fourth time, something like 500 times better than a single limited 8-meter telescope. And you gain in angular resolution, because that, again, also goes with diameter. So your images are much, much sharper, 15 times better than Hubble, 6 times better than James Webb. I'm sure you've seen these things when James Webb came in, and they were doing this banner. They were saying, oh, Hubble versus James Webb. Oh, watch how much sharper it is. That's only a factor 2.5. Imagine a factor 2.5 goes to 15, how much sharper that image is. And you can do this with the ELT at James Webb. You can really peer into the building blocks of galaxies, stars, and the future. So the ELT, I'm conscious about the time. ELT is a facility. And what we provide is not an experiment, but a facility. So it has been thought from the very beginning to provide science as broad as you can. And that's why the telescope does something, but then we can keep providing new instruments depending on the necessity of the community. So at the moment, we have these instruments, but we can keep developing others as we go along to do even more science. And this goes from planets, stars, galaxies, cosmology. And what I want to do is to give you just a small flavor of which science the ELT has been thought today to do. But I'm expecting that the young generation, so you guys at the back there, you come up with new ideas. So that's what has been thought in the past. But what we want to know is the unknown. So what else can the ELT do? So let me go say, don't stop at this. Think what comes after this, okay? So I give you what we thought today, and we're going to do the first couple of years, but I really need you to come with something new on top of this to what do we do. So one of the key science that's been driving the ELT is certainly the characterization of exoplanet atmosphere, because we are discovering many of them, but what we want to do is to really understand what is the capability of this planet to host life, essentially, right? The Nobel Prize in 2019 was awarded to two astrophysicists, Michel Mayor and Didier Queloz, for discovery of the very first exoplanet, and that they received the Nobel Prize for this. Since then, we have been discovering planets almost every day. So we have more than 6,000 of them already confirmed. And you can see here distribution across our part of the galaxy. Mostly are nearby, but there are some pencil beam surveys that can go further away into the galaxy for it. But that is a discovery. So once you know a planet is there, what you want to know is characterizing it, understanding how this planet are, how they are formed, can they host life? And we do this through spectroscopy by looking, for example, at the atmosphere. So if you have a star here and the planet goes around it and passes in front of the star, at some point, the light of the star passes through the very, very thin atmosphere. Now, imagine you have a massive star, a small planet goes in front of it, and a very thin few kilometers, maybe a couple of kilometers atmosphere imprints some spectrum, some features into the spectrum. So you need a very, very high sensitivity to do this. That's where the ELT comes in, and also very good resolving power, because what you want to do is detecting biosignature. For example, if you, in the spectrum, you see the typical features of a dead planet, for Mars or Venus, where you have only some of the things that it tells you that the planet does not have life. But if you find some of the features which are similar to what we have on Earth, and we know that some of these features can only be built by some kind of life, that is a biomarker that tells you that that planet might have light. It doesn't tell you there is life on the planet, but there might be light, or it's possible to host life in the planet. So on the ELT, because we have this very high angular resolution and very high sensitivity, we are capable of looking to these very, very thin things that happen into the planets. So this is an example of a simulation using METIS for a planet going around Alpha Centauri, very close to us. And in just 2 hours is able to detect if there is a planet at 1 AU. So 1 AU far away in a star which is 4 light years away from us, we will be able to see and measure the characteristic of this planet, both with METIS in the mid-infrared, but also in the visible near-infrared with the METIS. But we can do also spectroscopy of this, particularly with Andes, where we have this 100,000 resolution. We can pierce into the atmosphere of this planet and understand if there is any biomarker for this planet. So super exciting science. But also, we're looking at resolved stellar population. We want to understand how our own stars form. And that's where, again, the sensitivity and angular resolution of the ELT comes into play. When you are in crowded regions, when you have many, many stars nearby, if you have very low angular resolution, everything is blurred together. And therefore, the bright star will cover completely the faint one nearby. That's an example of James Webb NIRCam versus Mikado. It's the same patch of the sky, observed with both. But because you have a lower angular resolution, you can see some of those blobs that are a single blob in James Webb, it break down into 3, 4, 5 objects. And that gives you 3 magnitude gain just purely for confusion limited. So you go down much more in understanding the star formation in terms of imaging. And of course, you can do spectroscopy, both with Mosaic, with Andes, to get medium and high resolution spectroscopy out into nearby galaxies, not only our own, and also in very dense region of the central part of galaxies. And then we want to push this to the edge of the universe. And again, ELT will be able to resolve every single galaxy because the diffraction limit is so small that you can get not only the building blocks, the giant molecular clouds in these distant galaxies at redshift 2, but also in imaging, but also in spectroscopy to get the physical and chemical properties, but also the dynamics. So you will be able, if these early systems are rotating or they're puffed up by dynamical pressure. And in terms of diffraction limit of the ELT, this equates to 50 to 100 parsec scale at redshift 2. So what do we do today in the local universe? We'll be able to do it at 10 billion years away from us in terms of resolution of the building block of the galaxy. And there's Eros likes, so you can push this a factor 10 better if you use lensed objects. So if you take an object which are lensed by some intervening cluster, you can push this even smaller and go down to parsec scales at redshift 2, which is more than what you can do today in the local universe. Then we can look at supermassive black holes. And in 2020, there was a Nobel Prize award for the discovery of a supermassive compact object in the center of our galaxy. And how that was done over the last 15 years was using a star called S2, which orbits with a period of 16 years around this mysterious central black hole. And what you do is this star is the brightest, so the only one bright enough that we can observe at this orbit. And the orbit is small enough for us to keep repeating this. When the star goes nearby the massive object, what it does, you're not in a Newtonian gravity field anymore, so the orbit itself changes due to GR. And what we do today is to track the star, but because Mikado on the ELT has got much more angular resolution and sensitivity, we can look at stars which are even closer, fainter on what we can today, and go even closer to the central potential field of the black hole, and therefore see even if GR works or not at those level of accuracy compared to what we can do today. We can push this into dark matter. Again, sensitivity, angular resolution. You can do rotation curves of galaxies, both in the inner core to see if it's a cusp or flat, and also in the outer part, because you have sensitivity to see also very far out. So you can sample both the inner core and the outer part of a galaxy to really trace the profile of the dark matter and see as across the cosmic time if there is a change in the gravitational, in the components of dark matter, which today we know we have rotation curves that are very flat outside, but we don't know if in the early universe, the properties of dark matter were different or not. We can push this to even fundamental physics. So we learned at uni that there are some things in the physics books which are constant. For example, the fine structure or the ratio of the mass of the proton and electrons. And these are assumptions. We know that we assume that these are constant. But with ELT, we have enough resolution to see in the distant universe by looking at some light of quasars if some of the lines are shifted compared to what we have in the lab to an accuracy of 10 to minus 6. One part in 10 to minus 6, to see if this constant are really constant also in the early universe. And if they are not, we have to rewrite the book of physics, right? So we have to change our physics to make sure that this accommodates this part. And finally, we also have one test, which is called the Sandwich test, to watch the expansion of the universe in real time. Many of the way in which we infer that the universe is expanding is through indirect things, from supernovae or BAO, while with ELT is sensitive enough. If we observe a quasar, a redshift 3 or 4, we observe it today and we observe in 10 years from now, and we maintain the instrument stable enough, which is not easy, but we can do it. We might be able to see the expansion of the universe in live, essentially. So we can see that redshift happening in real time in 10 years. So sensitive is the telescope. And that would be a completely independent, model independent test of the expansion of the universe. So that is all what ELT can do. But because we are almost completing the ELT now, at ESO we are thinking what's happened next. And that is really for the young generation from 2040 plus. ESO has started last year a new initiative, which is called Expanding Horizon, what comes after the ELT. And here is where we really need your input. What is the science, the key science in 20 years from now? It's not 5 or 10, 20 years from now. What do we need? After we have the ELT and we have solved some of these questions, what do we need next? So it's going to be a call for preparatory phase up to mid of next year, then a call for ideas the year after, and then some assessment and a decision on how ESO would continue after the completion of the ELT. So I really encourage everyone to do this, to engage, to have ideas to do this. And I stop here and I leave you with a video, which is a time lapse of the last couple of years of the ELT as has been constructed across the various bits from the central part to the dome and the structure itself. And I stop here.
Thank you very much, Michele, for such an exciting talk, really impressive. So once more, remarking the great synergy between science, technology, industry. I also appreciated the synergy between astronomy and gastronomy when you thought about the use of zero dur for the kitchen. So for the cooking, let's say. So yes, so it's open now for questions. So please ask any question to Michele. Let's take this occasion.
Or ideas from the young people.
Or ideas for young people, yes. Carlo? No, over there, yeah.
Maybe.
Thanks, Michele. So what are the biggest advancement in technology, engineer, to go from VLT to ELT that you can discuss now? What are the things that we have learned, or people doing and constructing this telescope have learned from VLT to ELT?
So everything for the ELT has been an R&D development. So all the control part of the mirrors, for example, how you build a mirror, how you control them. We went to industry and we said, we need this product. They said, we don't have it. So let's sit together. Let's have an R&D program. And then we do this. Sometimes we had to merge companies. One company could do one part of it, and the company could do another part of it. We merge them together, have a new company now, which is the merge of the two, to develop the product that we need. They've been learning on how to polish the mirror in such a large scales, which is now be sold to other telescopes. We have a lot of software being developed in terms of real-time computing, very, very fast computation for the things. All the instruments are developing different type of optics. So it's a engineering endeavor across everything. So the people that built the dome main structure is an Italian company. It was Astaldi and Cimolai. Then Astaldi was out. We have Cimolai, which is an Italian company from Pordenone. They were building bridges before, bridges and stadiums. So now they've used this as their flagship. So we don't do only static parts. We also do dynamical things. They had to learn how to move such a big structure, but very, very accurately. They had to develop anti-seismic things underneath, because Chile is a seismic thing. So they had to invent essentially a new way of damping the earthquake for such a big structure. And now they have they have a patent for this kind of things. All the ESO engineers have been trying to help these companies developing new things, developing new strategies to do things. So it's been a big, big endeavor, and we're still fixing things today. So I would say a bit of everything.
Okay.
Thank you for the very nice talk. It feels like it's a golden era to be an astronomer. I wonder about some problems that we are facing at all wavelengths, which are constellations. So, I mean, we could see very sharp images, but if there will be the constellations, ruining them, how ESO is facing this issue and what can we do?
So for the ELT in particular, we'll be looking at the impact of this satellite constellation coming in. And because the field of view is relatively small, the chances of one of the satellites today is quite low. But for telescope like LSST or for FORMOST, which the field of view is square degrees, that's where the impact is. So there's been an attempt to discuss with the companies to coat the satellites with the anti-reflective thing. So the problem for us is mostly at twilight, beginning of the night, end of the night, when they are close by, so the light of the sun goes in and comes back to us. So there's been an attempt, which has been received quite well, at least by one of the companies, to make this coating outside that does not impact too much. This is also a problem for the radio frequencies, right? So it's not only for the visible, but also for the radio, where it's much more difficult to screen these signals that they send. So the problem is not today, is every single country and every single company starts sending up thousands of the satellites, then even for the ELT will be a problem. So they go quite fast across, they will disturb some things, but if you get many of them, it's a problem. So for the visible infrared, the idea is to suggest them to coat the outer part so they don't shine back. For the radio, is going to be some other solutions. I don't know which one.
Given that when they built the VLT, they decided to build 4 of them, and given that the ELT is relatively cheap, and the pressure is going to be incredible because everybody wants to use it, is there any plan for like maybe building a couple more of ELTs once you're done with the first one?
Come to the next horizon. So that it can be one of the possibilities, right? Some of the cost of the ELT of 1.5 billion is in design, right? So once you have design, when you build a second one, it's going to be cheaper. So one of the possible ideas for the new horizon is, why don't you build 2 more ELTs? Therefore, you remove the pressure on the observations. Think that we are in 2040, so the VLT by then is going to be 40 years old. So you can think about some kind of future in that direction. But 1.5 billion for ESO is a significant amount of money. So it's the equivalent of a large mission for ESA. And in terms of budget for ESO is what you can afford in one shot. You could not build 2 ELT at the same time. So you have to be one, and then you see the next.
Thank you for the nice and inspiring lecture, Christmas lecture. You mentioned multi-messenger science, and for this, I mean, many targets are transient, explosive targets. What are the performances in repointing fast for ELT? I mean, is there this option to repoint fast? 5 minutes.
5 minutes. But it's mostly as soon as you decide, now I observe. If I have to go somewhere far away, it's 5 minutes. If you are nearby, it's even quicker. But the 5 to 6 minutes is, I need to preset now anywhere in the sky with an instrument which is already on the right platform. So this is the big thing. Because we have M4 and M5. M5 is pointing towards one platform. If I have to turn to the other platform, that takes 15 minutes. So you add 15 minutes if you want to change instruments for which is already working now, essentially. But we thought about this transient universe already into the system. So you point, the telescope acquires, then the instrument closes the loop on AO, and then you go for it. You have to prepare the OBs, you have to do some, if you're quick in those few minutes, let's say, within half an hour, you are on target. By the time you trigger, you get the approval for do it. There is these things of pre-approval, TO, time for opportunity. So within several tens of minutes, 10, 20 minutes, you should be on whatever targets you want. So
that. You mentioned the moon. Is there any idea to go to the moon with the telescope and spend less than such a huge project?
I think is not feasible in terms of budget. So the ESO projects are over the other 1 billion. Going to the moon is a much, much bigger endeavor. So at the moment, I don't think it's feasible. In the future, we see.
Okay. More questions for Michele? And if you want to think of more questions,
there are questions from
online. Okay, so please.
I don't see that.
Hello, my name is Maria Stone, and I am from ENAF EOPS. I'm a postdoc right now supporting work for upcoming moons. So it's my first postdoc, and I wanted to know, in addition this, first of all, thank you so much for this inspirational lecture, and also for letting us know about this January workshop. Sounds amazing. But in order to get more ideas, it would be nice to have some initiatives and programs to support traditionally underrepresented minds from humans in astronomy. Can you expand a bit how early career scientists are supported specifically by ESO coming, like, is there any future programs to align for that, especially from member states and different backgrounds? If there are more talent is tapped into, I believe more amazing discoveries will happen. Thank you.
So we have an ESO fellowship, so it's open to everyone. You can apply. So we are in the selection for this year is already closed, but for next year, this is ESO fellowship where everyone can apply, young research career, they can apply and see if they go through the selection process.
Okay, I think there is one more question online. Maria? No?
Sorry, I just asked my question. Thank you for answering. I hope there are more supportive programs to, because ESO fellowship is amazing, but has been there for a while. So something else needs to change to increase the representation of women in astronomy.
We try to always improve the STEM, so that's a normal things we do at ESO in terms of ecosystem. So we are supporting all of it. So.
Okay, other questions from online? I don't see any hand raised. So I have a question personally, Michele, sorry. Let me just ask
the privilege of the
least, last but not least, hopefully. So I'm more expert in dealing with ESA, European Space Agency. So even though, as you mentioned, many colleagues here and the observatory in Bologna are working and making this great contribution to ESO, which are very proud of. So from the programmatic and funding point of view, when dealing with ESA and the science program of ESA, it's always things look always very complicated, a lot of uncertainty, especially now. If you think of the history of Athena, for instance, terrible. So the impression, let's say, from outside, from scientists not strictly working with ESO, is that ESO is somewhat more robust from the point of view of funding and programmatics. Is this correct, or is it just an impression?
Of course it is.
Of course it is. Of course, this is okay. Yeah.
No, so what we have are programs. So ESO, usually we start something when we have the funding for it. So in that sense, it's quite conservative. Like the Americans tend to do, I have a bit of money, I spend, I have a bit of money, I spend. For ESO, the policy is you need to have the funding. So for the telescope, there was a cost of completion that was allocated to the construction of the telescope. That is what is going on for that program. For the instrumentation program that I have a budget line per year. And we start new things only when we know there is a wedge into the spending profile, so we can start something new. We also have our own hiccups. So some of the instruments are more expensive than what you initially thought. We try to maintain contingency. We try to see if we can, through the funding agencies, get some of that money back. We try to control this. So we are cautious on what we start and try to support them until the very end. And also ESO is, it's quite strong in what we do in terms of delivering ESO to the telescope operation-wise. So in that sense, is a robust way of proceeding.
Okay, thank you very much. Other two questions there?
Hi. First of all, I have to say it was a great pleasure to listen to you today.
Thank you, Maria.
And, in a futuristic view, I would like to know, how do you plan to operate the telescope? Already the VLT, every second, I remember, loss of time need to be indicated. It was a big problem. So we have to save time. Can a human being run the VLT, or in the future will be better to have a program hybrid machine with AI, artificial intelligence, to operate the telescope for not losing either 1 second of it. So, we have seen recently the robot of Elon Musk can even cook meal. So
yeah. So what we started is a program within ESO, which was IOP, Integrated Operation Program, which is looking at operating the VLT and ELT in as smart, as efficient, as maintainable possible system. So they're looking at processes internally on how you do maintenance, on how you operate, if you can do remote observations as much as you can. They're looking at AI as well. So Today, what we're trying to do is not to say, oh, I know how to operate VLT, I do the same and I apply the same to ELT. No, there's been a complete revision on how VLT and ELT will be operated as part of the observatory, trying to optimizing processes, reducing cost, improving maintenance, and reducing the downtime. So preventive maintenance, a lot of these kind of things are in place at the moment. Oh, we're looking at this now.
Okay. More questions? So if there are no other questions, I thank Michele again on behalf of all of us. Thank you so much again. So, and wish all of you a happy Christmas break. Thank you very much again.